Tonight's lecture is over Chapter 1, Scientific Thinking. In this chapter, we'll learn how to define science, define biology, describe scientific thinking, describe key aspects of well-designed experiments, describe how scientific thinking can be used to help make better decisions, and describe the major themes in biology. Did you know that you are already a scientist? You may not have realized this yet, but it's true. Because humans are curious, you have no doubt you've asked yourself or others questions about how the world works and wondered how you might find the answers. For instance, have you ever wondered if the radiation released by cell phones can cause brain tumors? Have you ever wondered if antibacterial hand soaps are better than regular soap? These are important and serious questions, but you've probably pondered some less weighty issues too, like for instance, why is morning breath so stinky? Why is it easier to remember gossip than physics equations? And if you really put your mind to the task, you'll start to find questions all around you whose answers you might like to know. Here's something important to know. Science does not require advanced degrees or secret knowledge dispensed over years of technical training, but it does require an important feature of our species, a big brain, as well as curiosity and a desire to learn. Ultimately, though, curiosity, casual observations, and desire take you only so far. Moving on, science is not simply a body of knowledge or a list of facts to be remembered. It is an intellectual activity encompassing methodical, objective observation, description, experimentation, and explanation of natural phenomena. Put another way, science is a pathway by which we can come to discover and better understand our world. But we ask the question, how do we know what is true? This is one question you can and should ask about the scientific claims that you see on products or read about in the newspaper or on the internet. For example, after fortifying Rice Krispies and Cocoa Krispies with vitamins, the Kellogg Company made claims that its cereals help support children's immunity. Was this true? After an outcry by nutrition experts and in response to an investigation by the Federal Trade Commission, a U.S. government agency with the mission of consumer protection, Kellogg removed the claims and agreed to advertising restrictions. In this and many other cases, dubious, unsupported, or false product claims have been removed only because people pose the important question, how do you know that is true? Using scientific thinking, the claims were then put to the test and wound up being disproven. Notice, however, we never prove it right. Suppose you invent a good guess, calculate the consequences, and discover that every consequence you calculate agrees with the experiment. Does that mean that the theory's proven right? No, that simply means it is not proven wrong. Because in the future, there could be a wider range of experiments, you could compute a wider range of consequences, and you may discover that the thing is wrong. That is why laws like Newton's laws for the motion of planets last such a long time. Basically, Newton guessed the law of gravitation, calculated all kinds of consequences for the solar system, compared them to an experiment, and it took several hundred years before the slight error in the motion of Mercury was developed. During all that time, the theory had been failed to be proven wrong and could temporarily be taken to be proven right, because tomorrow's experiment may succeed in proving what you thought was right wrong. Therefore, we are never 100% sure we are right. We can only be sure that we are wrong. Alas, our focus in this book is on biology, which is the study of living things, not on the motions of the planets. Taking a scientific approach, we investigate the facts and ideas in biology that are already known and study the process by which we come to learn new things. In the process of reading, you will learn exactly what it means to have scientific proof or evidence for something. As we move through the book, we'll explore more important questions in biology. What is the chemical and physical basis for life and its maintenance? How do organisms use genetic information to build themselves and to reproduce? What are the diverse forms of life on Earth, and how has that diversity arisen? How do organisms interact with each other and with their environment, etc.? Moving on, in this chapter we explore the specific methods used in scientific thinking and how to make use of the knowledge we gain to make smart decisions. Scientific literacy is a general evidence-based understanding of the basics of biology and other sciences. It is increasingly important in our lives, and literacy in matters of biology is especially essential. Although the examples of scientific thinking presented in this book vary greatly, but they all convey a message that is key to scientific thinking, and that is, it's okay, in fact, and usually necessary, to be skeptical. Moving on, a brief glance at any newspaper or media story will reveal just how necessary scientific literacy has become. Many important health, social, medical, political, economic, and legal issues pivot on complex scientific data and theories. For example, how reliable is DNA fingerprint evidence? Why do allergies strike children from clean homes more than children from dirty homes? And why do new agricultural pests appear faster than new pesticides? Moving on, as we progress in our study of biology, we will be developing biological literacy, that is, the ability to firstly use the process of scientific inquiry to think creatively about real-world issues that have a biological component, secondly, to communicate these thoughts to others, and thirdly, to integrate these ideas into your decision-making. But biological literacy doesn't involve just the big issues facing society or just abstract ideas. It also matters to you on a personal level. Should you take aspirin when you have a fever? Is it a good idea to consume moderate amounts of alcohol? Lack of biological literacy will put you at the mercy of quote-unquote experts who may try to confuse you or convince you of things for their personal gain. Scientific thinking will help you make smart decisions for yourself and for society. So the take-home message is, through its emphasis on objective observation, description, and experimentation, science is a pathway by which we can discover and better understand the world around us. And also to make smart decisions, biological literacy is essential. So section 1.2 is on page 4 of your book, and this figure on the right-hand side of the slide is figure 1.3 on the same page. Science method may sound like a rigid and linear process to follow, much like following a recipe, but by making the process sound inflexible, the phrase science method can also cause people to imagine and mistakenly imagine that it can be applied only to a narrow range of questions. However, in practice, the scientific method is highly flexible and often a nonlinear process that can be used to explore a wide variety of thoughts, events, or phenomena, not only in science, but in other areas as well. For this reason, rather than framing it narrowly as the science method, when appropriate, we will refer to this process by the more accurate term, scientific thinking. So you must be familiar with the 5 basic elements of scientific thinking. 1. Make observations. 2. Formulate a hypothesis or make a guess. 3. Devise a testable prediction. 4. Conduct a critical experiment. And 5. Draw conclusions and make revisions. Keep in mind that once the process of scientific thinking begins, it doesn't necessarily continue linearly through the 5 non-overlapping steps. Sometimes, initial observations lead to more than one hypothesis and several testable predictions and experiments. Often, the conclusions drawn from experiments suggest new observations, refinements to the hypotheses, and ultimately, increasingly precise conclusions. Moving on, a key characteristic of scientific thinking is that it is empirical. Empirical knowledge is based on experience and observations that are rational, testable, and repeatable. Another important aspect of scientific thinking is that it is self-correcting. As we continue to make new observations, we might find that we need to reject or alter a hypothesis about how the world works. This may be the most important feature of scientific thinking. It tells us when we should change our minds. Here's another take-home message for you. Scientific thinking is an empirical process that involves making observations, articulating hypotheses, generating predictions, designing experimental tests, and drawing conclusions. It is a flexible, adaptable, and efficient pathway to understanding the world in part because it tells us when we must change our beliefs. So let's talk about the first element of the 5 elements of scientific thinking, and that is to make observations. Scientific study always begins with observations. We simply look for interesting patterns or cause and effect relationships. A great deal of creativity of science comes from this type of activity. For example, the U.S. Justice Department reviewed 28 criminal convictions that had been overturned by DNA evidence. It found that in most of the cases, the strongest evidence against the defendant had been the eyewitness identification. This finding constitutes an observation, namely that many defendants who are later found to be innocent were initially convicted based on eyewitness testimony. The opportunities for other interesting observations are practically unlimited. Using scientific thinking, we can and will investigate other questions generated in response to intriguing observations. So our take-home message from this section is that scientific thinking begins by making observations about the world. And while we're making these observations, we note any apparent patterns or cause and effect relationships. And that brings us to element 2, which is the formulation of hypotheses. So based on observations, we can develop a hypothesis. A hypothesis is a proposed explanation for an observed phenomenon. So what hypothesis could we propose about the eyewitness testimony observations described in the previous section? We could start with the hypothesis, quote-unquote, eyewitness testimony is always accurate. We may need to modify our hypothesis later, but this is a good start. To be most useful, a hypothesis must accomplish 2 things. First, it must establish an alternative explanation for a phenomenon. That is, it must be clear that if the proposed explanation is not supported by evidence or further observations, a different hypothesis is a more likely explanation. Secondly, it must generate testable predictions. This characteristic is important because we can evaluate the validity of a hypothesis by putting it into a test. This is, in fact, how science commonly advances. We disprove hypotheses, which serves to increase our confidence in the alternative explanations. For example, we could disprove the eyewitness testimony is always accurate hypothesis by demonstrating that in certain circumstances, individuals who have witnessed a crime might misidentify the criminal. Moving on, researchers often pose a hypothesis as a negative statement, proposing that there is no relationship between 2 factors, such as echinacea has no effect on the likelihood of catching a cold or the duration of cold symptoms. A hypothesis that states a lack of relationship between 2 factors is called a null hypothesis. However, both a hypothesis asserting some sort of relationship and a null hypothesis proposing no relationship are equally valid, but typically it is more straightforward to disprove a null hypothesis. Any new observation that contradicts a null hypothesis can be sufficient for the researcher to reject it and conclude that an alternative hypothesis must be considered. Conversely, and as I stated earlier, it is impossible to prove that a hypothesis is absolutely and permanently true. All evidence or further observations that support a hypothesis are valuable, but future evidence may show that the hypothesis is not true. Nonetheless, as more and more evidence supporting a hypothesis accumulates, our confidence increases that it is a true and accurate explanation for the phenomenon. So moving on, for the question about echinacea and illness, we could state our hypothesis in either of these ways. Echinacea reduces the likelihood of catching the common cold and the duration of the symptoms of a cold. Or the null hypothesis, echinacea has no effect on the likelihood of catching the common cold or the duration of the symptoms of the cold. So our take-home message from this section is that the hypothesis is a proposed explanation for an observed phenomenon. Moving on, not all hypotheses are created equal. A useful hypothesis helps us make predictions about novel situations, and it guides us to knowledge about new situations. When we devise a testable prediction from a hypothesis, our goal is to propose a situation that will give a particular outcome if our hypothesis is true, but will give a different outcome if our hypothesis is not true. So let's examine this concept. The hypothesis is eyewitness testimony is infallible. The prediction is, regardless of how suspects are presented, individuals who have witnessed a crime will correctly identify the criminal. This is a good, testable prediction because if our hypothesis is true, then our prediction will always be true. On the other hand, if one method of presenting suspects consistently leads to the incorrect identification of the criminal, our hypothesis can be not true and must be revised or discarded. So let's talk about another hypothesis. Echinacea reduces the likelihood of catching the common cold and shortens the duration of the symptoms of a cold. The prediction is, if echinacea reduces the likelihood of catching the common cold and shortens the duration of the symptoms of a cold, then individuals taking echinacea should get a cold less frequently than those not taking it, and when they do get sick, their illness should not last as long. As you begin to think scientifically, you will find yourself making a lot of if-then types of statements. If that is true, referring to some hypothesis or assertion someone makes, or perhaps a claim made by the manufacturer of a new health product, then I would expect proposing your own prediction about a related situation. Once you've made a testable prediction, the next step is to test it. And once again, we'll summarize this section with a take-home message. The take-home message is, for a hypothesis to be useful, it must generate a testable prediction. And this leads us to our fourth element of scientific thinking. Once we have formulated a hypothesis that generates a testable prediction, we conduct a critical experiment, an experiment that makes it possible to decisively determine whether a particular hypothesis is better than the alternative hypothesis. Many crucial elements go into designing a critical experiment. But for now, let's just say it is important to just understand that a critical experiment allows us to make observations that compel us to reject alternative hypotheses while not ruling out the particular hypothesis being tested, or vice versa. When engaging in this element of scientific thinking, a bit of cleverness can come in handy. So let's test our hypothesis. Eyewitness testimony is always accurate. First, we stage a mock purse snatching in front of a group of observers who do not know the crime is staged. Next, we ask observers to identify the criminal. To one group of observers, we present 6 suspects all at once in a lineup. To another group of observers, we present the same 6 suspects one at a time. The beauty of this experiment is that we actually know who the criminal is. We can evaluate with certainty whether an eyewitness's identification is correct. This exact experiment has been done, but with an additional twist. The researcher did not include the actual criminal in any of the 6-person lineups or the one-by-one person presentations of the 6 suspects. And we'll continue this discussion in the next section. But for now, let's test the hypothesis that we were talking about concerning echinacea by conducting a critical experiment for it. So the hypothesis is, echinacea reduces the likelihood of catching the common cold and shortens the duration of cold symptoms. Researchers performed an experiment with 437 people who volunteered to be exposed to the viruses that cause the common cold. All of the volunteers had cold viruses suspended in a watery solution dripped into their noses. The research participants were then scheduled in hotel rooms for 5 days, and doctors examined them for the presence of the cold virus in their nasal cavity and for any cold symptoms. Note that this is actually unusual to expose human participants to illness for research purposes, and they must always be informed of the risks and sign a form given a type of permission called informed consent. But before the cold virus treatment, the volunteers were randomly divided into 4 groups. In 2 of the groups, each individual began taking a pill each day for a week prior to exposure to the virus. Those in one group received echinacea tablets, while those in the other group took a placebo. And this is important. Neither the participant nor the doctor administering the tablets knew what the tablets contained. In the other 2 groups, the individuals began taking the tablets on the day of exposure to the cold virus. Again, one group got echinacea and the other group got the placebo. And here is your take-home message for this section. A critical experiment is one that makes it possible to decisively determine whether one hypothesis or an alternative is supported by evidence. And that brings us to our 5th element of scientific thinking. Once the results of a critical experiment are in, they are examined and analyzed. Researchers look for patterns and relationships in the evidence. They draw conclusions when possible and see whether their findings and conclusions support their hypothesis. If an experimental result differs from what is expected, that does not make it a quote-unquote wrong answer. Science includes a great deal of trial and error. If the conclusions do not support the hypothesis, then researchers must revise the hypothesis, which may lead to more experiments. This cornerstone of scientific thinking demands that you be open-minded and ready to change what you think. The surprising results of the purse snatching experiment illustrate this idea. When the suspects were viewed together in a lineup, the observers or witnesses erroneously identified someone as the purse snatcher about 1/3 of the time. When the suspects were viewed one at a time, the observers made a mistaken identification less than 10% of the time. And remember, in this experiment, the lineup did not include the actual quote-unquote criminal. So in this or any other experiment, it does not matter whether we can imagine a reason for the discrepancy between our hypothesis and our results. What is important, though, is that we have demonstrated that our initial hypothesis, which was eyewitness testimony is always accurate, is or is not supported by the data. Our observations suggest that at the very least, the accuracy of an eyewitness's testimony depends on the method used to present suspects. So, based on this result, we might adjust our hypothesis to something like eyewitness testimony is more accurate when suspects are presented to witnesses one at a time. Then, we can devise new and more specific testable predictions. In the case of eyewitness testimony, further investigation has suggested that when suspects or pictures of suspects are placed side by side, witnesses compare them and tend to choose the suspect that most resembles the person they remember committing the crime. When viewed one at a time, suspects can't be compared in this way, and witnesses are less likely to make misidentifications. But let's go back to our discussion of the echinacea study. The results were compelling. Those who took the echinacea were just as likely to catch a cold as those who took the placebo. In addition, once they caught the cold, the symptoms lasted for the same amount of time. In short, echinacea had no effect at all. Several similar studies have been conducted, all of which show that echinacea does not have any beneficial cold-fighting effects. Thus, it seems clear that our initial hypothesis, which was echinacea protects people from catching colds and reduces the duration of cold symptoms, is not correct. Further experimentation, however, might involve altering the amount of echinacea given to the research volunteers or the length of time they take the echinacea before being exposed to the cold-causing viruses. The outcomes in these studies illustrate that after the results of a critical experiment have been gathered and interpreted, it is important not just to evaluate the initial hypothesis, but to also consider any necessary revisions or refinements to it. By revising a hypothesis based on the results of experimental tests, we can explain the observable world with greater and greater accuracy. So our take-home message from this section is that based on the results of experimental tests, the conclusions we draw may necessitate revising our hypotheses and, in the process, help us understand the observable world with increasing accuracy. Moving on. What are the elements that make up a well-designed experiment? In this section, we'll explore some of the ways to maximize an experiment's power to help us discern causes and effects. First, let's consider some elements common to most experiments. Treatment is any experimental condition applied to the research participants. It might be the pattern used to show the quote-unquote suspects, all at once or one at a time, to the witness of the staged crime, or the dosage of echinacea given to an individual. The experimental group is a group of research participants who are exposed to a particular treatment. For example, the individuals given echinacea rather than the placebo in the experiment described earlier. It is sometimes referred to as the treatment group. A group of research participants who are treated identically to the experimental group, with one exception, they are not exposed to the treatment, is called the control group. An example would be the individuals given the placebo rather than the echinacea. Variables are the characteristics of an experimental system that are subject to change. In an experiment, the variables can be described as either independent or dependent. An independent variable is some entity that can be observed and measured at the start of a process and whose value can be changed as required. As an example, the independent variable might be the amount of echinacea a person is given. On the other hand, a dependent variable is one that can also be observed and measured, but whose response is created by the process being observed and depends on the independent variable. A dependent variable in the echinacea study might be how long the symptoms of the cold last. Moving on, when we speak of the quote-unquote controlling variables, we are describing the attempt to minimize any differences between a control group and an experimental group other than the treatment itself. That way, any differences between the groups and the outcomes we observed will most likely be due to the treatment. Okay, this is figure 1.10 on page 11 of your book. This figure illustrates a real-life example of the importance of considering all of these elements when designing an experiment. Just for a little background, stomach ulcers are erosions of the stomach lining that can be very painful. In the late 1950s, a doctor reported in the Journal of the American Medical Association that stomach ulcers could be effectively treated by having a patient swallow a balloon connected to tubes that circulated refrigerated liquid. He argued that by supercooling the stomach, acid production was reduced and the ulcer symptoms were relieved. The doctor had a convincing data set to back up his claim. All 24 of his patients who received this quote-unquote gastric freezing treatment experienced an improvement in their condition. As a result, the treatment became widespread for many years. So we have a clear hypothesis here. That is, gastric cooling reduces the severity of ulcers, and there are some compelling observations. For instance, there are 24 patients that experienced relief. However, this experiment was poorly designed because it lacked a control group with which to compare the patients who received the treatment. And this slide is the second half of figure 1.10. So a few years later, another researcher decided to do a more carefully controlled study testing the same hypothesis. He recruited 160 patients with ulcers and gave 82 of them the gastric freezing treatment. The other 78 received a similar treatment in which they swallowed a balloon but had room temperature water pumped into it. The latter was an appropriate control group because the participants were treated exactly like the experimental group, with the exception of a single difference between the groups, whether they experienced gastric freezing. The new experiment could test for an effect of the gastric freezing while controlling for the effects of the other lurking variables that might affect the outcome. The researcher found that 34% of those in the gastric freezing group saw an improvement in their condition, but surprisingly, 38% of those in the control group also improved. In other words, gastric freezing didn't confer any benefit when compared with a treatment that did not involve gastric freezing. Subsequently, the practice of gastric freezing was abandoned soon after the publication of these results. Moving on, the placebo effect is frequently observed but poorly understood. It is a phenomenon in which people respond favorably to any treatment. The placebo effect amplifies the need for an appropriate control group. If the control group receiving the placebo or sham treatment has an outcome much like that of the experimental group, we can conclude that the treatment itself does not have an effect. Moving on, in designing an experiment, it is important to withhold from a participant any information that may influence him or her. This particular kind of experiment is called a blind experimental design. This can reduce biases that may arise from the participants' expectations. For example, in a blinded experiment conducted by Fugate Instruments concerning the tonal quality of gold anodized vibraphone bars versus silver anodized vibraphone bars, highly accomplished vibraphonists could not tell any difference in tonal quality between the two colors of bars. In order to prevent the musicians from guessing the color of the vibraphone bars, the researchers asked them to wear a blindfold and sit with their backs to the vibraphone, while another accomplished vibraphonist played instruments with the different colors of bars on them. Another potential pitfall in designing an experiment is that persons conducting the experiment may influence the experiment's outcome, and this could even be unintentional. This effect was seen in a study of dental patients following an extraction under anesthesia of a molar. In one experiment, the patients were given either a placebo or a powerful painkiller without knowing which they were given. In another experiment, the patients were given either the placebo or a different drug that does not reduce pain, again without being told which they received. In the first experiment, patients receiving the placebo reported a significant reduction in their pain. In the second experiment, patients receiving the placebo reported a large increase in their pain. So why did the placebo have an effect in one experiment but not the other? Well, in the first experiment, the dentist who was administering the drug knew that the patient might possibly receive an actual painkiller. But in the second experiment, the dentist knew that there was no chance that the patient would receive a painkiller. The results highlight the value of the double-blind experimental design, in which neither the experimental participants nor the experimenter knows which treatment a participant may or may not be receiving. And yet another hallmark of a well-designed experiment is that it is randomized. In this context, randomized refers to the fact that the research participants are randomly assigned to the experimental and control groups. With this approach, researchers and research participants have no influence on the composition of the two groups. The use of randomized, controlled, double-blind experimental design can be thought of as an attempt to design the experiment to account for all the possible ways that someone might criticize an experiment so that the results cannot be explained by anything other than the effect of the treatment. In this way, the experimenter's results either support the hypothesis or invalidate it, in which case the hypothesis must be rejected or modified. If multiple explanations can be offered for the observations and evidence from the experiment, then it has not succeeded as a critical experiment. So our take-home message is that in order to draw clear conclusions from experiments, control and experimental groups should differ only with respect to the treatment of interest. Differences in outcomes between the groups can then be attributed to the treatment. Moving on, in 2001, the journal Behavioral Ecology changed its policy for reviewing manuscripts that were submitted for publication. Its new policy instituted a double-blind process whereby neither the reviewers nor the authors' identities were revealed. Previously, the policy had been a single blind process in which reviewers' identities were kept secret but authors' identities were known to the reviewers. An analysis of papers published between 1997 and 2005 revealed that after 2001, when the double-blind policy took effect, there was a significant increase in the number of published papers in which the first author was female. Analysis of the papers published in a similar journal that maintained the single-blind process over that period revealed no such increase. The study illustrates that people, including scientists, may have biases, sometimes subconscious, that influence their behavior. It also serves as a reminder of the importance of proper controls in experiments, in this case using a double-blind approach to reduce the potential impact of biases. Moving on, another important element of scientific thinking is replication, the process of repeating a study. This is an experiment that can be done over and over again by a variety of researchers and gives the same results each time. This is an effective defense against biases. Furthermore, when experiments are repeated and the same results are obtained, our confidence in them and the hypotheses associated with them increases. Additionally, sometimes a tiny variation in the experimental design can lead to different results. This can help us isolate the variable that is primarily responsible for the outcome of the experiment. Our take-home message is that biases can influence our behavior, including our collection and interpretation of data. With careful controls, it is possible to reduce the impact of biases. Moving on, it's an unfortunate source of confusion that among the general public and in the popular media, the word theory is often used to refer to a hunch or a speculation or a guess. That is, something we are not certain about. In fact, to scientists, the word means nearly the opposite, and that meaning is a hypothesis of which they are most certain. In order to reduce these common misunderstandings, we examine here how scientists describe our knowledge and natural phenomenon. So as we have already seen, hypotheses are at the very heart of scientific thinking. A hypothesis is a proposed explanation for a phenomenon. A useful hypothesis leads to testable predictions. Typically, when non-scientists use the word theory, for example, like, I've got a theory about why there's less traffic on Friday mornings than on Thursday mornings, they actually mean that they have a hypothesis. A scientific theory, on the other hand, is an explanatory hypothesis for natural phenomena that is exceptionally well supported by empirical data. A scientific theory can be thought of as a hypothesis that has withstood the test of time and multiple experiments and is unlikely to be altered by any new evidence. Like a hypothesis, a scientific theory generates predictions and is testable, but because it has already been repeatedly tested and no experimental results have contradicted it, a scientific theory is viewed by the scientific community with nearly the same confidence as a fact. For this reason, it is inappropriate to describe something as quote-unquote just a theory as a way of asserting it is not likely to be true. Theories in science also tend to be broader in scope than hypotheses. In biology, two of the most important theories are cell theory, which states that all organisms are composed of cells and all cells came from pre-existing cells, and the theory of evolution by natural selection, which asserts that differential reproductive success based on heritable variations leads to change in populations. So our take-home message is that scientific theories do not represent casual guesses about the natural world. Rather, they are hypotheses, proposed explanations for natural phenomena that have been so strongly and persuasively supported by empirical observation that the scientific community views them as very unlikely to be altered by new evidence. Moving on, let's look at the data. Whether they are making a point, illustrating an idea,
or facilitating the testing of a hypothesis, visual displays of data condense large amounts of information into a more easily digested form. In doing so, they can help readers think about and compare data, ultimately helping them synthesize the information and see useful patterns. Among the multitude of ways to display data, a few forms are used more frequently. These include bar graphs, line graphs, and pie charts. Visual displays of data generally have a few common elements. Most have a title, which usually appears at the top and describes the content of the display. Bar graphs and line graphs include axes, usually a horizontal axis, also called the x-axis, and a vertical axis called the y-axis. Each axis has a scale, generally labeled with some gradations, indicating one dimension by which the data can be described. The x-axis of a line graph, for example, might be labeled time spent studying each day, while the y-axis might be labeled performance on midterm exams. Depending on the size of the data set, individual data points may be included on the graph, with additional information conveyed by the shape, color, or pattern of the data points. A line or curve may be used to connect the data points or to illustrate a relationship between the two variables, and the axes must always be labeled and include the units of measure. Rather than displaying an individual data point, a bar graph has rectangular bars, each with a height proportional to the value being represented. In a pie chart, each slice is a proportion of the whole. A legend or key may be included for the graph, identifying which information is represented by which data point or bar or pie slice. And this slide simply shows an example of a line graph. Moving on, one of the most common functions of visual displays of information is to present the relationship between two variables, such as in a graph. As we discussed in section 1.8, an independent variable can be changed by the experimenter as required, while the dependent variable is one whose response is created by the process being observed and depends on the independent variable. The dependent variable is generally represented on the y-axis and is expected to change in response to a change in the independent variable, represented on the x-axis. The number of hours of sleep a student gets each night, for example, could be thought of as an independent variable, while some measure of academic performance, maybe grade point average, would be the dependent variable. Moving on. Visual displays of data may have features that reduce their effectiveness or even cause them to be downright misleading. These difficulties can arise from ambiguity in the axis labels or scales, incomplete information on how each data point was collected and how the points might have been varied, biases or hidden assumptions in the presentation or grouping of the idea, unknown or unreliable sources of data, or an inappropriate context given for the data presentation. So our take-home message is that visual displays of data can aid in the presentation and exploration of the data. Their effectiveness is influenced by the precision and clarity of the presentation and can be reduced by ambiguity, biases, hidden assumptions, and other issues that reduce the viewer's confidence in the underlying truth of the presented results. Moving on, statistics is a set of analytical and mathematical tools designed to help researchers gain insight from their data that they have gathered. This can help with understanding the data as well. Suppose you measured the height of two people. One is a woman who is 5 foot 10 inches tall, and the other is a man who is 5 foot 6 inches tall. If these were your only two observations of human height, you might conclude that female humans are taller than males. But suppose you measured the height of 100 women and 100 men, chosen randomly from a population. Then you would find that for the 100 men, the average height is 5 feet 9.5 inches, and for the 100 women, the average height is 5 foot 4 inches. Better still, With 100 measures for each sex, the data can illuminate not only the average but also some measure of how far the typical observation is from average. One such measure is called the standard deviation. You may find that not only is the average height for a man in this study 5 feet 9.5 inches, but that the standard deviation is 3 inches. This may be stated as 5 foot 9.5 inches plus or minus 3 inches. That data might also show that for the woman, the average height is 5 foot 4 inches plus or minus 2.5 inches. In graphs, the standard deviation or some other indication of the amount of variation in the population is commonly depicted as lines or a shaded region extending above and below the average. One handy mathematical property of the standard deviation is that for a normally distributed set of observations, about 2/3 of the observations will be within one standard deviation above or below the average. In other words, about 2/3 of the men are between 5 feet 6.5 inches tall and 6 feet 1/2 of an inches tall, and about 2/3 of the women are between 5 foot 1.5 inches tall and 5 feet 6.5 inches tall. Moving on, using data to describe the characteristics of individuals participating in a study is useful, but often we want to know whether data support or does not support a hypothesis. For example, suppose we want to know whether reading the textbook helps a student perform better in a biology class. Statistics can help us answer this question. After conducting a study, suppose we find that students who read the textbook scored an average of 81% plus or minus 8% on their exams, while those who did not scored an average of 76 plus or minus 7% on their exam. In this example, it is difficult to distinguish between the two possible conclusions. Possibility 1. Students having access to a textbook perform better in biology class. Our sampling of this class reveals a true relationship between the two variables, that is, textbook access and class performance. After all, 81% is better than 76%. Possibility 2. Students having access to a textbook do not perform any better in biology class. The variation in scores for the two groups may be too large to allow us to conclude that there's any effect of having access to a textbook. Instead, the difference in average scores for the two groups might mean that more of the high-performing students just happened, through random chance, to be in a group given access to a textbook. Moving on, but what if the students with access to the textbook scored, on average, 95% plus or minus 5%, while those without access scored only 60% plus or minus 5%? In this case, we would be much more confident that there is a significant effect of having access to a textbook, because even with the larger variation in the scores seen in each group, the two averages are still very different from each other. So statistical methods help us to decide between these two possibilities, and equally important, to state how confident we are that one or the other is true. The greater the difference between two groups, example, 95% versus 60%, is greater than the difference than 81% versus 76%. And the smaller variation in each group, plus or minus 5% in the 95% and 60% groups versus the plus or minus 8% and plus or minus 7% in the 81% and 76% groups, the more confident we are of the conclusion that there is a significant effect of the treatment. In other words, in the case where the groups of students scored 95% or 60%, depending on whether they did or did not have access to a textbook, it is still possible that having a textbook did not actually improve the performance, and that this observed difference was just the result of chance. But this conclusion is very unlikely. Moving on, statistics can also help us identify relationships or lack of relationships between variables. For example, we might note that when there are more firefighters at a fire, the fire is larger and causes more damage. This is a positive correlation, meaning that when one variable, that is the number of firefighters, increases, so does the other, the severity of the fire. Should we then conclude that firefighters make fires worse? No. While correlations can reveal relationships between variables, they do not tell us how the variables are related or whether change in one variable causes change in another. In other words, correlation is not causation. To estimate the effect of the number of firefighters on the amount of damage, we would need to compare the amount of damage from fires of similar size that are fought by different numbers of firefighters. Ultimately, statistical analyses can help us to organize and summarize the observations that we make and the evidence we gather in an experiment. These analyses can then help us to decide whether any differences we measure between experimental and control groups are likely to be the result of treatment and how confident we can be in that conclusion. So our take-home message is that statistics can help us evaluate whether any differences between a treatment group and a control group can be attributed to the treatment rather than chance. Moving on, one of the major benefits of scientific thinking is that it can prevent you from being taken in or fooled by false claims. Two types of falsely identified, quote-unquote, scientific evidence are cited in the popular media frequently and are responsible for people erroneously believing that two things are linked when in fact they are not. One is pseudoscience, in which individuals make scientific-sounding claims that are not supported by trustworthy, methodical scientific studies. And there are also anecdotal observations, in which, based on just one or a few observations, people conclude that there is or is not a link between two things. Pseudoscience is all around us, particularly in the claims made in marketing and on the packaging of consumer products and food. Pseudoscience capitalizes on the belief shared by most people that scientific thinking is a powerful method for learning about the world. Pseudoscience consists of statements made to appear as if they are based on factual scientific evidence when they are not. Likely, we are all familiar with anecdotal evidence. We may find compelling parallels between suggestions made in horoscopes and events in our lives, or we may think that we have a lucky shirt on that helps ensure our favorite sports team will win the game. That's how superstitions develop. So our take-home message is that pseudoscience and anecdotal observations often lead people to believe that links between two phenomena exist when in fact there is no such links. Moving on, scientific thinking gives us a framework to make sense of what we see, hear, and read in our lives. However, there are limits to what science can do. The scientific method will never help us understand the mathematical eloquence of Fermat's last theorem or the beauty of Shakespeare's sonnets. It won't prove or disprove the existence of God, nor can it address the ethical question of whether we should allow the cloning of humans. Scientific thinking differs from non-scientific approaches such as mathematics and logic and the study of artistic expression in that it relies on measuring phenomenon in some way. The generation of value judgments and other types of non-quantifiable subjective information falls outside the realm of science. Scientific thinking does not, for example, generate moral statements, and it cannot give us insight into ethical problems. What is not necessarily what ought to be. Also, much of what is commonly considered to be science, such as the construction of new engineering marvels or the heroic surgical separation of conjoined twins, is not scientific at all. Rather, these are technical innovations and developments. While technology relies on sophisticated scientific research, it represents the application of research findings to varied fields such as manufacturing and medicine to solve problems. The take-home message is that although scientific thinking is an effective path toward understanding the observable world, it cannot give us insights into value judgments and other non-quantifiable subjective information. Moving on, biology is literally the study of life. But what is life, and how is it distinguished from non-life? Scientists have grappled with these curiously difficult questions for hundreds of years, and disconcertingly, the more of the Earth's diversity we discover and study, the harder the task of defining life gets. Moving on, while we try to define life, we have characteristics that are shared by all living organisms and living systems. There's order, there's the use of energy, there's responsiveness to the environment, there's regulation or homeostasis, growth, development, and reproduction, and evolution. And also, there are 5 central themes in biology. One is evolution. The second is structure and function. The other is information flow, exchange, and storage. Another one is pathways and transformations of energy and matter. And the 5th one we label as systems. And the take-home message from this section is that life is not easily described with a simple definition, but rather is identified by the presence of certain characteristics shared by living organisms. Although the field of biology is broad, it has 5 organizing themes that are important in unifying diverse topics.